In this video, we're going to see how we can solve a simple linear programming problem by drawing the feasible region and finding the extreme points. So we have this formulation for our simple maximization problem. Our approach, if we want to solve this problem by drawing, would be to find the feasible region. What we can do here, when we want to solve it, we need to find all those combinations of S and D, standard bag and deluxe bag, all those combinations of S and D that works in all the constraints that we have, which basically is called a feasible solution. So we need to find all the feasible solutions, anything that satisfies all the constraints. And once we have the set of feasible region, we go ahead and find the best one and call it the optimal solution. All right, so our first concentration should be on finding the feasible solution, anything that satisfies all the constraints of the problem. And then once we have that, once we have the feasible region as the set of all the possible solutions, all the feasible solutions, we just need to find the best solution. In the case of a maximization problem, we need to find the feasible solution with the highest objective function value. So that should be our objective. So I'm going to come back here. So what I'm going to do, I'm going to draw just one of these constraints, just to give you the idea of how we draw the feasible region. And then we can, I'm just going to show you the graph that actually has all these 6 constraints. So here we have 6 constraints, right? One for cutting and dyeing, one for sewing, finishing, inspection and packaging, and then we have 2 non-negativity constraints. In total, 6 constraints. Each constraint, when we have the constraints, as you can see here, they're all of our 4 constraints are in inequality forms. When we have constraints in equality forms, what they do, they actually cut this space into half spaces. And then only one of these half spaces is going to be feasible. The other one is going to be infeasible. The intersection of all these 6 half spaces, in our case, we have 6 constraints. So we will have actually 12 half spaces. Maximum 12 half spaces. The intersection of the 6 half spaces, the 6 feasible half spaces are going to make our feasible region. So I'm going to just show you the, I'm just going to draw 3 of them. Maybe 3 easiest one. So I'm going to do sewing, and I'm going to do the non-negativity constraint. So I'm going to write it down here. So half of S plus 5/6 of D less than or equal to 600, D greater than or equal to 0, and S greater than or equal to 0. So if I come here, of course, I know that there are 6 constraints, but here we just want to understand how we can, how we can find these 3, and then we can just keep going and do it for all these 6. So here, D and S, if we just do, if we consider the whole space, where, for example, S is on the horizontal axis and D is on the vertical axis. This one, I'm just going to start with these two, and then we can draw this one, and then we can keep going for the other three constraints. D greater than or equal to 0. So this means, so this is the D, this is the axis for D. Any point above this line, this horizontal line that passes through origin, any point above this line is actually has D value greater than or equal to 0. Any point above this line, this horizontal line, all right? S greater than or equal to 0. Any point on this space that is to the right of this axis, to the right of the vertical axis, any point that you actually consider, S is either positive, or if they're on the line, on the vertical axis, their S is equal to 0. So any point on the line or to the left of the line will be feasible, and any point to the left of this line would be infeasible with respect to this constraint. Any point above this line is feasible with respect on and above this line is feasible with respect to this condition. Any point below, strictly below this point, is infeasible with respect to this constraint, right? So now, I mean, if I'm just going to consider these two, so far, the intersection of these two subs or half spaces would be this region, this quarter of the space. This is the feasible region where both S and D are greater than or equal to 0. All right. Now I'm going to draw this one. So for this one, I need to find the line. I need to, like here we had the line, we had the axis, and it was very easy. We could just, if D want to be greater than or equal to 0, the line would be D equal to 0, right? So that would be the boundary for this one, for this. So D equal to 0 is this line. D0 is this line, and then any point above it would be feasible. Any point below it is not feasible. Same thing, same concept applies here. We need to find the line that actually holds true when we have equality here. So we need to find, we need to first find the line with this equation, half of S plus 5/6 of D equal to 600. So we just need to find this line, and then at one side of this line, we will have feasible solutions with respect to these constraints. At the other side, it's going to be infeasible. In order to draw a line, we need to get 2 points. We just need to find 2 points, and when we connect these 2 points, we will get the line actually on our graph. So here, I just need 2 points. I can do this. So if I put D equal to 0, S will be 1200. If S is 0, D is going to be S0, D is going to be 720. So I just need to find these 2 points on my space and connect those. So S, I'm just going to assume it's here. And then let's say 600, 200, 400, 600, 800, 1000, and 1200. So this is my point 1. And on D, let's say 200, 400, 600, and then 720. 720. Let's say this is 720. D 720. This is going to be my point. So I just need to connect these 2 points. All right. So now I have the boundary line for this constraint. So I have the boundary line. This is the line. So at one side of this line, it's going to be feasible with respect to this inequality. At the other side, it's going to be in violation of this inequality. So in order to check, you can just put the origin when S and D are 0. So if you put 0 and 0 here, the origin, when we just look at this constraint, origin 0 and 0 is feasible. 0 plus 0 less than or equal to 600. So this 0, the origin is at the feasible side of this inequality. So therefore, any point below this line or to the left of this line would be considered feasible. So this would be half of S plus 5/6 of D less than or equal to 600. So far with these 3 constraints that we have, we just need to keep going. We need to draw the other lines for the other 3. But so far for these 3, this is my feasible region so far, which is the intersection of these 3. If we keep going, if we just do it for the other constraints for cutting and dyeing, we just did it for sewing. If we do it for finishing, cutting and dyeing, and inspection and packaging, we will get a graph like this one. We will get a graph like this one. So what we just did was this one, 1200 and 720 for sewing. And we already know that the lower side is feasible. And if we just keep doing for finishing and inspection and packaging and cutting and dyeing and find the intersection of all these 6 constraints or 6 half spaces, this blue region is where all these 6 constraints are satisfied. This is the intersection of all these 6 half spaces. So this is actually the set of, or the feasible region, the set of all the solutions that are possible. They're not violating any of our constraints. So those are any point in this. If we just take any point in here, we're not violating any of our constraints, which means that they're good. They're possible to be implemented, considering our constraint. Now we need to find the best out of this feasible region. First of all, before we talk about that one, this feasible region always, when you have your inequalities, when you have your constraints in linear format, when you have all of them in line, the intersection of these half spaces is always convex, meaning that if you take any 2 arbitrary point in this region and connect those, the connecting line is going to be inside the feasible region. So I'm just going to show you an example of here a set that is not convex. So this is convex, meaning that if you take any point here with any other arbitrary point, and if you connect those 2 points, any point on this line is also within the region, within the convex region. But for example, for this one, if you take this point and if you take this point, the connecting line there are a piece of it that is not within the region. So this is not convex. So by definition, when you have all your constraints in linear format and in inequalities, you will have a convex set of feasible region, which makes it super easy for finding the optimal solution. Now, for our objective function, we had the objective function was 10s plus 9d, all right? But we didn't have any specific value for that. If you take 10s plus 9d equal to a constant number, that would give you the equation for a line again. So it's going to be a line. You can just put an arbitrary number. So let's say 5,400 and draw the line. Any point on this line, any point on this line, as long as it's within the feasible region, as long as it's in the blue region, so we don't care about this part, we don't care about this part, any point, any S and D on this line, if you take any of those, the value of objective function is going to be 5,400. And if you increase this for the 5,400 a little bit, it's going to be another parallel line, the equation of another parallel line, but to the right of this point, right? And you can keep increasing this value. And at some point, actually the equation, the line that you draw is gonna cross the feasible region only in one point, only in one extreme point, in one corner. And then after that, you won't be able to increase the value of your objective function, basically. So if this would be, if you just put 76, 69, then the line will be outside of the feasible region, meaning that there's no point in the feasible region that can give you a profit of 76, 69. The best value, the largest value for your intercept, or for the value of your objective function, can go all the way up to 76, 68. And after that, it's not possible. So this is your clue that this value is going to be our optimal profit, the value of objective function when you have the optimal point. And then the corner that gives you that value is going to be your optimal solution here, optimal solution. I said we have a convex feasible region, since we have, since all our constraints are in inequality here, it's gonna always be convex, a convex set, meaning that if you take any 2 points and if you connect those, it's going to be the actually connecting line is going to be within the feasible region. And because of this feature, a convex set, a convex feasible region can be defined by a set of corners. And corners are intersection of boundary lines, basically, right? Boundary spaces, boundary conditions. So here we have how many corners? 5 corners. 1, 2, 3, 4, and 5. So corners can be intersection of 2 or more boundary conditions. So now, here in this example, the optimal solution happened to be at corner 3 or extreme point 3. All these basically intersection of these boundary conditions are called extreme points or corners. So this happened to be in the corner. The optimal solution happened in this example happened to be in a corner. In reality, we can actually prove this is actually a very nice feature that is used for finding the optimal solution as fast as we can using the software. And the method is actually called simplex method. By this feature, by this property, we just need to check the value of objective function on the corners. So basically, if you don't need to really find the feasible region, like you don't need to check the value of objective function in any value in any of these points on the feasible region. As long as you have the corners, you can check the objective function on the corners and just compare those and basically find the optimal solution. Simplex method is even simpler, is even faster. You just start from one of these corners and go to the connecting corner and go to the next corner and check to see if you can go to the next corner or not. So in this case, you just move to this point by 2 iterations, here to here and here to here, and you check that basically you won't be able to go to a better point. So you stop here at this point and you call this your optimal solution.